Moving on is topic 6, multiple and logistic regression. Actually, there are two concepts in this module. The first concept is multiple linear regression. It's still linear. And then the second concept is logistic regression. So the goal or the learning outcomes of this module is to learn how we can come up with multiple variable linear regression. And then since we have multiple independent variables, what would be the coefficient? Before this, we were using Pearson for one independent variable, but now we have multiple independent variables. So how do we estimate the coefficients for this situation? And then number 3, to make inferences in multiple regression, that means we need to have hypothesis testing, confidence intervals for the coefficients. And then number 4 is another different subtopic. How do we turn linear regression into logistic regression? And what is logistic regression? Why do we use logistic regression? Examples of usage of logistic regression, such as risk assessment, classification problems, predictive analytics. Okay, maybe you already have a child, maybe no. But if you have a child, you'll be wondering how tall your child will be in the future. According to Johns Hopkins medicine, there is a formula to determine the height of your child. The main factor will be the height of both biological parents. So if you want to know how tall your child will become, then you need to measure your height and your wife's or your husband's height. And then the other factor is whether the child is a male or female. Yeah, because this is another factor. If the child is male, then the height will be, of course, usually will be taller than the female. Yeah. So according to Johns Hopkins, for male children, you add 5 inches to the father's height, and then you add to the mother's height, you divide by 2. For female children, you will deduct 5 inches from the father's height, add mother's height, then divide by 2. However, according to Johns Hopkins medicine, this predictive methods is not final, it's not concrete, because a child's adult height could change depending on other factors. Yeah. So as I mentioned, linear regression formula, right, is just an estimate because that estimate will be true if we're able to cover all the factors. But if we are covering only some part of the factors and there are other factors unknown, we still can use it, but we use the error term to cover the possible deviation. So let's look at how we can turn this to a formula. Now, a male child, okay, as mentioned by the algorithm just now, if a male child, the father's height plus 5 inches plus the mother's height divided by 2. If daughter, you minus 5 inches from the father's height. Again, repeat the same thing. If we want to consider gender as a factor, then this is what is going to happen. The child's height, 0.5 height of father, 0.5 height of mother, plus 5 times the gender of the child. If 0, assuming that the variable G 0 is for female and 1 for male, minus 2.5 error factors. That means there are other unknown factors, maybe diet and other factors unknown. Yeah. This one is based on the sampling. So this can be the formula that we use to predict the height of the child with factors such as the father's height, mother's height, and the gender of the child. So as you can see in the previous formula, right, the height of the child is determined by more than one predictors: father's height, mother's height, and the gender. So there are 3 predictors here. So this is what we mean by multiple regression. Yeah, it is an extension of simple linear regression because actually the formula is very much the same. If you look at the simple linear regression, you have y given by beta naught plus beta 1 multiplied with the first factor x1. But in multiple linear regression, you have more than one axis. Yeah, x1, x2, x3, and so on and so forth. Thereby, we have slopes for each of the factors because not all factors are equal. No factors are equal. You know, some factors have more impact, some factors have less impact. So the slope will determine how much impact that the factor has on the outcome, which is y. Yeah. A part of multiple linear regression, we also have more polynomial linear regression, whereby we have x squared, x cubic, so on and so forth. But this does not fall within the scope of this course, so we're going to skip this. But this is just to let you know, multiple regression also covers multiple regression. And polynomial linear regression are related because they cover they encompasses they covers multiple factors, but polynomial is also considering the power or the power of the factors. Yeah, not just a single, but can cover quadratic, cubic, so on and so forth. Correct polynomial. Yeah, but let's forget this for now. We're just looking at the multiple linear regression. So let's compare the formula of simple linear regression and multiple linear regression. Just now I mentioned that multiple linear regression is an extension of simple linear regression. Therefore, the formula are very much similar. See, we are having more x's in multiple linear regression because there are more factors compared to simple. Simple assumes one factor only, but in multiple linear regression, we consider multiple factors, and each one is weighted by beta, beta 1, beta 2, beta 3. Yeah, and then visually, this is how the graph may look like if you have a multiple linear regression. So in this example, we have three factors, yeah, x, y, and z. Overall, the idea is the same. Overall idea is the same. It's just that we have extra dimension, yeah, extra dimension. And then in this case, beta 0 is the intercept with the y-axis. In this example, the intercept is 30. All right, and then depending on the location of the predicted y on the plane instead of line, because line is for simple linear model, but for multiple linear regression, it'll be on the plane. If it is 2D, it's guaranteed to be a flat plane. But if it's more than two factors, then the plane may not be a flat plane. It may have certain curvature to it. So in this example, the formula for the multiple linear regression, 30 is the intercept, B naught. And then we have x1. In this case, it's predicting no, x1 along the x-axis, okay, and then the weight is 5, and then we have x2, yeah, and it's weight of 7. And then here, as you can see, the plane actually represents the predicted value, and then yi here, the dot here is the actual value, and then the sigma I here represents the residual. Do you still remember what is residual? Residual means the distance or standard deviation. Standard deviation from the of the actual value versus the predicted value. Okay, as I mentioned just now, in multiple linear regression, we have more than one coefficients and more than one independent variables. We still retain error term because there always could be some factors that we overlook. Yeah, there could always be some factors that we have overlooked. So the beta 1, beta 2, the what we call coefficient, it represents the weight that affect how fast the y is how fast y changes when x is changing. For example, if beta 1 is 5, that 1 unit of increase in x1 will increase y by 5 units. Yeah. So if beta y is 100, then 1 unit increase in x will increase y by 100. So it shows that it has bigger impact. So as you should have known now, the purpose of multiple linear regression is to model multiple factors of influence, not just one factor, but multiple. And then for the very same reason, like in simple linear regression, you use multiple regression for predictions. Example, to predict a child's height, we have talked about it. Then the other example is to predict a calf, cow, to predict calf birth weight. So the formula given is beta 0 or beta naught plus B1 multiplied with weight of the mother plus B2 multiplied with weight of the father plus beta 3 multiplied with the gestation. Gestation is how many months of pregnancy. Because if the baby is born early, the weight is less. If the baby is born, the calf is born later on, then the weight is bigger. Yeah. Just one moment. Let me just one moment. I'll be right back. I'll be right back. Sorry, I'm right back. Just now I went out to collect something. Just a quick one. Sorry. Okay. Yeah. So it's very much like simple linear regression, but with more factors. Okay, let's move on to a new concept in Module 6 called Logistic Regression. As you have learned in linear regression, you use a straight line to find a model, a straight line model that can actually capture the relationship between X and Y. But it is not always linear. Sometimes it is a curve. So if you remember, maybe back in secondary school, you have played with this curving ruler, soft S-shaped ruler, yeah, that you can use to draw not a straight line, but a curved line. Usually it's looks like a U curve, N curve, or S curve, yeah. So logistic regression is a statistical algorithm which analyzes relationship between two data factors for classification tasks. The keyword here is for classification. Now let's compare the left chart and the right chart. The data are the same. The data are the same. That's why you look at the green plots. The green plots are the same. Yeah. But the model that we use is different. One is a straight line model. We use a straight ruler. The other one we are using the curve ruler. So the curve ruler, when you use it, you will get an S shape, because S shape probably if you use an S shape, you'll be able to overlap with you try to overlap with all the green dots. Yeah. Obviously, a straight line is not good because it just overlap with probably two dots. And then furthermore, the residual. So remember residual? Residual is the distance from the actual value from the expected value on the straight line. Straight line represents the expected value. So in linear regression, for this kind of graph, for this kind of plotting, the residuals will be very big because they are too far away from the straight line. Yeah, but if you change the straight line to S curve, you see you can minimize the distance or residual from the green dots to the red line. So apparently S curve is better to model this data set. All right. So get the idea about logistic regression. So logistic regression, the idea is to show classification, because when you see you have when you have an S shape, then you see that the top side may belong to one class. There's a cluster here, and then at the bottom there's another cluster, which is another class. So in logistic regression, we try to convert the values on the y-axis to be within the range of 0 and 1. Okay, so this will be binary classification. Yeah, this will be binary classification. So when do we use logistic regression? We model the probability that an instance belongs to a given class or not. The dependent variable is categorical, child, adult, senior citizen, or binary, yes, no, 0, 1. Example, predicting the probability whether the customer will buy a product or not. Oh, okay. I think a point of correction here. The dependent variable is categorical, and it must be binary. Sorry, so it's not like child, adult, senior citizen. There will be 3 categories already. For logistic regression, it will be binary, 2 categories only. All right. So there's a typo error here. Let me just fix it. It's binary. Just one moment. It's binary. Categorical. Yeah, because it is S curve, right? So you'll be only splitting the data into 2 clusters. So that's why it's binary. For example, customer will buy or not. You have 2 possible outcomes. Now, this happens, you need to use logistic regression instead of linear regression when the data on the y-axis is categorical, not continuous. If you have a continuous values on the y-axis, then you won't get a logistic pattern. You will get linear pattern. So obviously, linear model is not suitable for this data set. So let's take a look at this, how we can actually turn a linear, we can turn a linear equation to logistic equation. Yeah. We make use of sigmoid function. We make use of sigmoid function. When we make use of sigmoid function, we'll be getting a chart where the y value is within the range of 0 to 1. And then when the x is approaching 0.5, yeah, when x is approaching 0.5, then there will be a steep curve, a steep slope. Yeah. And then when the x is small, close to 0, or when x is close to 1, in sigmoid function, the value will exponentially go very, very small, especially go very fast. It will go very, very close to 1. Yeah. It will go exponentially on the extreme ends. So we use log for that purpose. We are converting the linear readings into curve. So this formula shows how a linear shape can be turned into sigmoid shape. Okay, using log. Okay. The logistic regression model transforms the linear regression function continuous value output into categorical value output. It uses a sigma function which maps any real valued set of independent variable input into a value between 0 and 1. Because if you use log, right, the value will always approach to 1. And then for a very small value, the value will approach 0. No matter what the value you put inside the log, yeah, the maximum is 1. Then the bottom is 0. So what is the formula for logistic regression model? It's given as follows. Yeah. Y over, 1 over 1 plus and natural log. And then you need to find the x value along the x-axis minus the location parameter. Location parameter is the midpoint of the curve. Yeah, midpoint of the curve. Okay, the midpoint of the curve. And then S is the scale parameter. Okay, so the threshold value here is the midpoint. Yeah, the midpoint. Because the midpoint here, the midpoint is the location on the x-axis where the y is 0.5. It's called midpoint because it's halfway between 0 and 1. Yeah, midpoint. So the purpose of using this regression model is to transform outputs into probabilities. Yeah, and then it uses maximum likelihood estimation instead of least squares. Least squares is when we are doing linear regression. Coefficient represents the log, log of odds. And then the estimate function where the input will be z, and we find the probability between 0 and 1 in y. For example, if a beta 1 is 0.7, then 1 unit increase in x1 increases our success by exponent 0.7. Yeah, because we are using a log for this. Okay, there are two formula for logistic regression. We can write it in this format where the z value, which is given by negative x minus mu divided by s, scale parameter. Yeah? Or we can replace the readings of x and mu with the coefficients beta 0 and beta 1. This can be acquired by using formula. Okay, and then what is S? S is scale parameter. It represents the dispersion of the logistic distribution, just like the standard deviation in a normal distribution. Okay, let's look at one YouTube video. Sorry, two YouTube videos on logistic regression to look at other explanations and examples of how logistic regression is used.
Logistic regression is a statistical technique that models the probability in events given one or more independent variables. You'll start with input data that is of any numeric type, but the output variable will be binary. It'll be 0 or 1, indicating a false or a true value respectively. You then fit this S-shaped curve called the logistic function to this data. It can then be used to make predictions of probability whether or not an event will happen, such as, given so many hours of rain, what is the probability of a flood? Notice how that these points can project themselves onto the logistic function, and we can use maximum likelihood estimation to fit the curve, which we'll talk about shortly. Notice that there are these middle points where there is a mix of true and false cases. If these points follow a transitional trend of increasingly showing an event more likely to happen or not happen, you will see that that S-shaped curve will climb or decrease respectively. We can then leverage it to predict probability between 0 and 1. Let's take a case where we expect 6.2 inches of rain, and this is going to result in a 0.75 or 75% probability of a flood. If we define a threshold, say 0.5, and anything greater than 0.5 will be true, anything less than 0.5 will be false, We will then predict there will be a flood. We can move this threshold based on our needs. For example, if we set it to 0.8, this would actually categorize as false and there won't be a flood. We can also reduce it to say 0.2 and set a much lower barrier to classifying a flood. This is the function that produces that S-shaped curve. E is Euler's number, which is a special constant. That beta 1x plus beta 0 is a linear function. That is actually the log odds function. That is something we will talk about in another video. What's important to know is that this function will produce that S-shaped curve we need to make predictions. We can also extend this to more input variables to create multi-dimensional logistic regressions as shown here. Let's talk briefly about maximum likelihood estimation. The way it works is that we are going to take each of these points, multiply their corresponding likelihoods together, and that is going to produce our total likelihood. We need to find the beta coefficients that will maximize the likelihood of our S-shaped curve producing all of these points. This can be done with gradient descent, Newton's method, and other optimization techniques. You might be wondering, why did I subtract the false cases from 1.0? This is because we have to treat the false cases as positive so that they are maximized as well. We will cover this on a separate video talking about maximum likelihood estimation in more depth. In a separate video, we will talk about how to handle false positives and false negatives, and we can use a confusion matrix as a tool to track prediction performance. Thank you very much for watching.
Okay, just this idea was logistic regression. Look at the second video, which is longer.
Welcome to this video about the basics of logistic regression. To understand the basics behind logistic regression, we'll first discuss the differences between linear regression and logistic regression. Remember that linear regression requires that the dependent variable, the one we put on the y-axis, should have a continuous scale. In this example, we like to predict how the prostate-specific antigen concentration in blood changes during aging. We have collected 8 individuals at different ages.
You see, this one is a linear regression. Distinct differentiator is that on the y-axis is a continuous data. It's not binary categories. It is continuous data. Yeah.
Measure their PSA levels. Note that this is just a fictive dataset created for the purpose of this video. For example, this person is 82 years old and has a PSA concentration of about 3.4 micrograms per liter. By fitting the linear regression model to the data, we can estimate the parameters B0, the intercept, and B1, the slope. For this example data, the intercept was estimated to 0.4 and the slope to 0.02. The estimated intercept tells us that a person at age 0 is estimated to have a PSA level of 0.4, whereas the estimated slope tells us that the PSA level increases by 0.02 each year.
So this part of the video is explaining back linear regression, how to interpret the equation. Then the video will talk about logistic regression, because the logistic regression is actually somewhat related to linear regression, and we need to know what linear regression is first. Then we'll be able to understand logistic regression better. So it talks about the beta 0 representing the intercept just now, and then beta 1, which represents the slope, how the weight of the age factor, how much it can impact on the blood pressure.
By using this equation, we can, for example, predict that a person with 80...
See, we can use linear regression for prediction because for the range where it is valid, right? Once we get the line, we can plug in any x value in order to get the y value. That's why it is a prediction. So in this case, If the person is 80 years old, then the blood pressure is 2.
Years old should have a PSA level of about 2 micrograms per liter. We can make the same prediction by drawing a vertical line where the x-axis is equal to 80, and then a horizontal line from the regression line to the y-axis. We see that by using the regression line, we can predict that a person at age 80 has a PSA level of about 2.
Now we're
Introduce
looking at the
logistic
logistic regression.
Suppose we have the following data. Note that this is just fictive data.
You see, this is different, right? For logistic, the y-axis, the data is categorical and it's binary. Yeah, for now, the limitation is that it's binary. Because we're using S shape, right? S shape has a bottom and the top. So the bottom and the top will be the two categories.
Data where the values have been selected for the purpose of this video. The variable on the y-axis is on nominal scale with only 2 categories. The variable on the y-axis represents if someone has prostate cancer or not. For example, these 7 individuals have prostate cancer, whereas these 7 individuals do not have prostate cancer.
Now, we know when we want to draw logistic regression, we are going to use the soft ruler to find the best S to represent the logistic line and the logistic curve. But the question is like, where is the S curve, right? As you can see here, there are some overlaps between the healthy and cancerous patient. So where is the best S curve? Where does the drop happen when it is 0.5? Because 0.5 is the threshold. Where is the sigma on the x-axis so that the p sigma, probably the sigma becomes 0.5?
Note that no data point can exist in this region since the y value has to be either yes or no. For example, this person has prostate cancer and a PSA level of about 3.8, whereas this person from the healthy control group has a PSA level of about 2.5. Let's change the labels on the y-axis so that 1 is used instead of yes and 0 is used instead of no. If you now try to fit a straight line to this data, it will result in a very bad fit.
You see, red line,
This
line
type of
wouldn't work.
data it seems better to fit an S-shaped curve that can only take values between 0 and 1. The following logistic function can be used, which can generate an S-shaped curve that is constrained between 0 and 1.
The S curve can be given by this formula, sigmoid formula. See?
When we use the
Where you see when you divide, you take 1 at the top, right? If you put 1 at the top, the maximum value will become if the denominator value is very huge, because we're using E, right? E is 2.7, and then on this side is the exponent, yeah, negative exponent. So the exponent will grow. We grow to become very, very small. Yeah, we go to become very, very small because it's negative. Where this will approximate 1, because 1 divided by 1 plus 0, it becomes 1. But if the the natural log becomes very, very huge, right? Then the division by 1 will yield 0. So this will limit cancer to between 0 and 1 only. Yeah, close to 0 and close to 1, but not exactly 0 and 1 because of the way this formula is done. If E is very, very big, then cancer becomes 0. If E is very, very small, then it becomes 1.
The logistic function for this kind of data. It is called logistic regression. We later see that the y-axis can be transformed into logged odds, which makes it possible to fit a straight line to the data. So far, we can conclude that the main difference between linear regression and logistic regression is that, first of all, in linear regression, the variable on the y-axis has a continuous scale, whereas in logistic regression, the variable on the y-axis has a numinous scale with only two categories. The second difference is that in linear regression, we fit a straight line to the data, whereas in logistic regression, we can imagine that we fit an S-shaped curve to the data. In another video, we'll cover the details of how the model is actually fitted to the data by the maximum likelihood method. We will now use the following dataset to see how the y-axis can be seen as a probability between 0 and 1.
So we are turning.
Note that we have a bit more.
So we are turning the y value for all the x reading to 0 and 1 only. Maximum 1, minimum 0.
Data points this
How to
time,
do that?
because it will help to explain how we can estimate the probabilities. Let's cut this plot into 6 pieces.
So why are my signals free? I get asked this question so many times. Why don't you charge any?
We then calculate the proportion of individuals within each range that has prostate cancer. For example, in the PSA range between 0 and 1, we have only healthy individuals, which means that we have 0% of individuals with prostate cancer. In the range between 1 and 2, 1 out of 5 or 20% have prostate cancer. And in the range between 2 and 3, 3 out of 6 or 50% have prostate cancer, and so forth.
See, at this point, the chances of having cancer and not having cancer is 50-50. You see? At this point, inside this red box, the chance is 50-50.
Let's create a plot where we show the fraction that has prostate cancer in these 6 ranges. We can add a point in this plot that shows that with a PSA level of 0.5, which is the midpoint in the first range, we have no prostate cancer patients. Then we add the point for the second range, where 20% of the individuals have prostate cancer. And then we add for the third range, and then for the other ranges. If you fit the logistic curve,
you see, by doing so, it looks like an S curve, right?
To these data points, the curve will fit very well to the proportions. We can use this curve to estimate the proportion that has prostate cancer in our sample. The curve can therefore be seen as an estimate of the proportion of individuals that have prostate cancer given a certain PSA level. For example, for a PSA concentration of 2, we expect...
So by having this curve, right, we can do prediction because we can just rely on this curve. We enter the X value, and then we can get the Y value, which is the probability of having prostate cancer.
That 20% of the individuals have prostate cancer. And for a PSA concentration of 3, we expect that about 70% of the individuals have prostate cancer. We can also think of the y-axis as the probability that a person has prostate cancer in this sample for a given PSA level. Note that the probability that you have a disease also depends on the prevalence. The predicted probability for a given PSA level is therefore only valid for this study group, where we have collected a certain number of patients with prostate cancer and a certain number of healthy controls. Watch the lecture about the positive and negative predictive value to see how the prevalence affects the probability that you have the disease, given a positive test. In this example, we see that the probability that a person with a PSA level of 3 has prostate cancer is about 70%. The logistic function that is used to draw this curve looks like this. The left-hand side represents the probability for prostate cancer for a certain PSA
This is the formula. You see beta naught and beta 1.
concentration. E is the Euler's number, which is approximately equal to 2.718. B0 and B1 are the parameters that we like to estimate, similar as we do in linear regression. By using a statistical software, we can compute the optimal values for B0 and B1 that gives us a good fit to the data. For this dataset, B0 and B1 were computed to -5 and 2. Let's plug in the values for B0 and B1 in the equation. With the help of this equation, we can now predict the probability that a person has prostate cancer given a certain PSA level. For example, if we set the PSA variable to 3, we see that the predicted probability that a person with a PSA concentration of 3,
PSA is the y-axis value. Yeah. Let's say put 3, plug in 3.
has prostate cancer is about 73%.
到底我是用 property Airbnb crypto 啊，买股票其实都不是，我是用
advertisement,
很多市场的工具。bro， 我跟你们讲啊。
We'll get the same prediction by using the plot if we draw a vertical line at 3 until we hit the curve, and then a horizontal line which intercepts the y-axis at about 0.73. We'll now use the following example data to explain how we can transform the estimated probabilities into logged odds. Note that we in this example have a bit fewer data points than in our previous example in order to simplify our calculations. In total, we now have 7 patients with prostate cancer and 7 healthy controls. For example, the first person in this dataset has prostate cancer and a PSA level of 3.8, whereas person number 8 is a healthy individual with a PSA level of 2.5. If you use logistic regression on the following data, B0 is now estimated to minus 5.75 and B1 to 2.75. By using this equation, we can compute the probability to have cancer for each person in the dataset given their PSA levels. For example, the estimated probability that person number 6 has prostate cancer based on its PSA level of 2.1 is about 0.5. We will get the same value if we use the fitted curve, since the curve has been generated based on the equation with the estimated parameter values. Let's compute these estimated probabilities for all individuals. If you now plot these estimated probabilities as points on the curve with x-coordinates that correspond to the corresponding PSA levels, the points will be located on the curve like this. The coordinates of these points correspond to the measured PSA levels and the estimated probabilities according to the logistic regression model. In this lecture, we'll not go into the details of how the probabilities can be converted into odds or logged odds. Instead, we just accept that the odds can be calculated like this. To calculate the odds, we divide the probability for having prostate cancer by 1 minus this probability, which corresponds to the probability of being healthy. For example, if we calculate the odds for person number 2 with a corresponding probability of 0.97, we get a value of 32.3. We can think of these odds as if we have 33.3 individuals with a PSA level of 3.4, one of these individuals will be healthy, whereas the other 32.3 individuals will have prostate cancer. Let's calculate the odds for the other rows as well, using the same equation to convert the probabilities into odds. Note that the odds have been calculated based on the rounded probabilities for the purpose of this video. Next, we compute the natural logarithm of the odds so that we get the so-called logged odds. We see that the logged odds will be negative if the odds is less than 1. And if the odds is greater than 1, the logged odds will be positive. If the odds is equal to 1, the logged odds will be equal to 0. As an example, the natural logarithm of 6.69 is about 1.9. Note that the probabilities take values between 0 and 1, whereas the odds may go from 0 to plus infinity. In contrast, the logged odds can take any values from minus infinity to plus infinity. Let's plot these logged odds so that we can see how the logged odds change over different PSA levels. Note that the logged odds seem to follow a straight line.
You see, the reason why we do a conversion, odds by itself is not so useful. Probability is useful because, like, for example, the first patient, right, he has a PSA of 3.8. So we have 99% probability of confidence that he will get cancer. But if we calculate the odds, right? The odds are actually not so useful. But odds is useful for getting the log odds. And why log odds is useful? What do you think? When we plot the log odds out, right? Log odds out. What do you get? You get a linear graph. A linear graph is nice because why? Because you can do easy plotting. You can because in linear graph, it's easier for you to calculate. Okay, let's say if the PSA is 3.5, what is the log odds? So you can get the log odds and you can work it backwards to get the probability.
For example, the predicted probability that person number 8 has prostate cancer is 75%, which corresponds to a logged odds of 1.1. We now fit a straight line to the data points. Note that the data points fit perfectly on the line.
The wealth of this world is temporary, but what you give to an orphan will be
Sorry,
counted for
X,
you
one moment.
in eternity. This Ramadan,
Remember that we used the following equation to fit the logistic curve to the data when the y-axis was expressed as a probability. The estimated values of B0 and B1 was minus 5.75 and 2.75. We can transform that equation so that the left-hand side is expressed at logged odds instead of a probability.
Now, this explains, you see, once you get this log odds, right, it will explain how to get the beta 0 and beta 1.
How we do this transformation will be discussed in another video. Note that the right-hand side now includes a linear term. This equation can actually be used to draw this line. We can now interpret the coefficients. Minus 5.75 is the intercept on the y-axis when the PSA concentration is equal to 0. The logged odds when the PSA level is equal to 0 is therefore estimated to minus 5.75. The slope of this line is 2.75. This means that if we increase the PSA level by 1 unit, the logged odds is increased by 2.75. Let's add two arbitrary points to this line. When the PSA level is equal to 3, the estimated logged odds is equal to 2.5, whereas a PSA level of 4 results in an estimated logged odds of 5.25. Then we antilog the logged odds of the first point, which results in an odds of 12.2. And do the same for the second point, which results in odds of about 190.6. We then calculate the ratio of these two odds, which gives us the so-called odds ratio. We see that the odds ratio is equal to 15.6. A faster way to calculate the odds ratio is to simply antilog the estimated value of the slope of the line. If we antilog the estimated value of the slope, we get the estimated odds ratio. Thus, the estimated value of the slope is equal to the logged odds ratio. This conclusion is important because it tells us how we should interpret the estimated parameters from logistic regression. For example, the odds for a PSA level of 4 is 15.6 times greater than the odds for a PSA level of 3. If we run logistic regression on our previous data in the statistical software, odds for a PSA level...
You see here, I elaborate what he said. Let's say we are looking at 0.1 and 0.2. Okay, 0.1 and 0.2. Now, the x value of 0.1 is 3. The x value of 0.2 is 4. Now, my question is, if for 0.1, what would be the y value? What would be the y value for 0.1 here? So you just use back the formula just now, because this one is a linear regression already, isn't it? From logistic, when we use log odds, right, we are converting the logistic graph into a linear graph. So just now, you can easily derive a linear graph from this, because you can just simply plot the linear graph. Yeah, you can simply plot the linear graph using the PSA and the log odds. Yeah, use the PSA and log odds. You can plot this graph. You can determine the interception. You can determine the slope using YMX plus C. Yeah, and then you get the formula. Negative 5.75, which is the intercept. 2.75 is the slope. Now, using this formula, you can work out the log odds value of 0.1 and log odds value of 0.2 given the S value of 3 and 4 respectively. That's why you get the 2.5 for 0.1 and 5.25 for 0.2. Yeah, which is the y-axis value. Okay. Now, once we get this 2.5, 5.25, so what? So what? Yeah, log odd is actually not very meaningful, but it's useful because it is a linear line, yeah, which is very convenient for calculation. So what? You see, the opposite of log odds, right? The opposite of log odds is natural log raised to the power of the value of the log odds, right? So if you are doing the opposite, because you want to get back the probability, you want to get back the odds. At first, you have the log odds value. You want to get back the odds value. So what you do, the log odds, right? You just use exponent natural log e raised to the power of the log odds. So you eventually get 12.2 for 0.1 and then 190.6 for 0.2. All right. And then the ratio of the odd ratio is given by 190.6 divided by 12.2. I can show how fast the odd increase with from 0.1 to 0.2, yeah, which is just one PSA increase. With just one PSA increase, it will increase 15.6 times. The odds will increase 15.6 times.
This conclusion is important.
In the face of evolving threats, protect every user journey. Introduce
expressed as the logged odds. If we run logistic regression on our previous data in the statistical software, we'll get an output that might look like this. The intercept in this case is of little biological interest, but we know that minus 5.75 represents the intercept on the y-axis expressed as the logged odds. The slope of the line is estimated to 2.75, which is our logged odds ratio. Since the corresponding p-value is less than 0.05, we know that the logged odds ratio is significantly greater than 0. If you anti-log this value, we'll get the odds ratio for 1 unit change in the PSA level. Remember that we can also calculate the probability for a certain PSA value if we plug in the estimated parameter values in our previous equation. If you plug in the estimated parameter values for B0 and B1, then we can, for example, calculate the probability that a person with a PSA level of 2.5 has a 75% risk of having prostate cancer in our sample. However, remember that the probability for having the disease given a certain test result is dependent on the actual prevalence, as we discussed in the lecture about the positive and negative predictive value. Also, since the PSA level is known to increase during aging, it seems reasonable to include the variable age in the model so that we can predict the probability of having prostate cancer based on both the PSA level and the age. We'll discuss logistic regression models with more than one explanatory variable in future videos. This was the end of this basic lecture about logistic regression. In other videos, we'll have a look at how logistic regression can be used as a classifier to, for example, tell if someone has a disease or not, and how to compute things like sensitivity and specificity and ROC curve based on logistic regression. In another video, we'll see how we can use the estimated odds ratio to...
I think we have achieved the objective of learning logistic regression. What is logistic regression? How to create a logistic regression model from the data, and how to use the logistic regression for prediction. And unlike linear regression, linear regression is for predicting a value when given a different predictors, a given different x value. We want to predict a y value. For logistic regression, we are not predicting a value, we are classifying. And please remember that the classification is binary. That means true, false, yeah, 0 or 1. It has many rooms for application. For example, predicting probability of equipment failure based on sensor data. Yeah, probability of this drug producing a positive effect on the patient. Either there's effect or no effect. These are all binary outcomes. And then we do not, however, we do not cover multiple factor for logistic regression. We only cover multiple factors for linear regression. So in a lot of situations, there are multiple factors leading to logistic regression. In machine learning, we use logistic regression a lot. In fact, the neural network is using logistic regression, using different kind of sigmoid functions to improve its classification ability. So the key points in module 6, we have learned about multiple regression, which is an extension of linear regression. Linear regression, a simple linear regression, is depending on only one predictor, only one x value. But multiple depends on more than one x value. Moving on, we learn about logistic regression. Logistic regression is used when we want to do prediction of category. We want to do classification. And the limitation is, however, it's only able to do binary classification. That means two two classification, yes or no. Yeah. We do not cover multiple logistic regression. However, it doesn't mean that multiple factor for logistic regression is not there. It is there. It's just that not covered in this lecture only. In machine learning application, probably you'll be looking at multi-factor for logistic regression. Both methods are widely used in predictive modeling. One for continuous data, you use linear regression, assuming that it is linear, and the other one for decision making, yes or no. Yeah, that's decision making. You may be wondering how is this related to non-parametric test. Now, in non-parametric tests, we are comparing sample populations. We are comparing samples or populations. Yeah, we may be comparing a sample with the expected population. We may be comparing two populations in terms of frequency. That is for non-parametric. Same goes for normal distribution, Poisson distribution. It's based on frequency. For certain value, how frequent. And for parametric, right? For example, Z value, student test, Poisson distribution. These are based on standard distribution. That means we know that this sample is following a known pattern. When it's based on a certain distribution, we are saying that it is following a known pattern. But for non-parametric distribution, it means that we are not sure, we do not know whether it's following any known pattern or not. So we use different formula to figure out, because when it's not following any known pattern, we won't have information about the population or known means, known standard deviation. We don't have this information, so we have to calculate it differently. That's why we have a different parametric tests in a non-parametric module. When it comes to linear regression and logistic regression, it's different ballgame. Even though it's also used for hypothesis testing, it's used for prediction. It can be used for hypothesis testing, just like previous modules. But the difference is that it's comparing, it's deciding whether there is a relationship between two variables or not. Previously, we are analyzing if the frequency of a pattern is observed or not. That was frequency. We are investigating the frequency for standard normal distribution, for non-parametric distribution. We are studying the pattern of the frequency. But in linear, we are not studying frequency. We are studying whether two different variables, is there any relationship between them or not? No relationship? Got relationship? If got relationship, is it positive relationship or negative relationship? And then in logistic regression, it's also the same thing, actually. Just that the difference is that logistic regression is for decision making. Instead of predicting Y value from X value, we are predicting the outcome, yes or no, from the X value. Logistic regression is similar to linear regression in many ways, except that it's using S-curve instead of line. Because you cannot do classification using line. You can only do classification using S-curve, because the bottom and the top of the S-curves are two different classes. The question is how to come up with those linear equation. How do you come up with those logistic equation? I've explained them in the lecture notes, as well as in the YouTube video that I've shared. I didn't repeat the effort because I believe that the YouTube video actually did a good job, but I just give a commentary along the way, and you can actually watch the YouTube video again and again to gain the understanding.